Let me define some of the peculiar terminologies mentioned in the context of Einstein's general theory of relativity and its implications for our understanding of gravity and spacetime. General theory of relativity, a fundamental theory of physics proposed by Albert Einstein, which describes gravity not as a force, but as a consequence of the curvature of spacetime caused by the uneven distribution of mass and energy. It generalizes special relativity and Newton's law of universal gravitation, providing a unified description of gravity as a geometric property of space and time. Spacetime, a four-dimensional continuum that combines the three dimensions of space, length, width, height, with the dimension of time into a single four-dimensional manifold. In the theory of relativity, the universe is described as a fabric of spacetime, which can be curved by mass and energy. Curvature of spacetime, the bending or warping of spacetime caused by the presence of mass or energy. This curvature is what we perceive as gravity, according to general relativity. Massive objects like stars and planets create significant curvature, guiding the motion of other objects and light around them. Gravitational waves, ripples in the fabric of spacetime that travel at the speed of light, generated by certain movements of mass, especially by cataclysmic events such as the merging of black holes or neutron stars. Their existence was predicted by Einstein's theory and has been confirmed by direct observation. Black holes, extremely dense regions in spacetime where the gravitational pull is so strong that nothing, not even light, can escape from it. The concept of black holes emerges from the equations of general relativity, describing regions of spacetime with extremely high curvature. Time dilation, a phenomenon predicted by the theory of relativity where time passes at a different rate in different gravitational potentials or at different velocities. In stronger gravitational fields, or at higher velocities, time is observed to pass more slowly relative to a weaker gravitational field, or lower velocities. Light bending, the deflection of light rays as they pass near a massive object, due to the curvature of spacetime around that mass. This effect, predicted by general relativity, has been observed during solar eclipses and in astronomical observations, confirming the theory's accuracy. Manifold, in the context of spacetime, a manifold is a mathematical space that might be complex and curved but locally resembles simply Euclidean space. Spacetime is considered a four-dimensional manifold in general relativity. Einstein's field equations, a set of 10 interrelated differential equations in Albert Einstein's theory of general relativity that describe how mass and energy determine the curvature of spacetime, which in turn describes the motion of matter and radiation. Now, to go back to the question, is gravity really exist according to Einstein's relativity? In Einstein's theory of general relativity, gravity is not described as a force in the traditional sense, as it was in Newton's law of universal gravitation. Instead, Einstein proposed that gravity is a manifestation of the curvature of spacetime caused by the presence of mass and energy. According to this view, massive objects like planets and stars curve the spacetime around them, and this curvature directs the path that objects take as they move. In essence, objects are not being pulled by gravity but are following the curved paths determined by the distorted spacetime geometry around massive bodies. This perspective significantly shifts the understanding of gravity from a force acting at a distance to an effect of spacetime curvature. Objects move through spacetime naturally following these curves, which is perceived as gravitational attraction. For example, the Earth orbits the Sun not because it is being pulled by the Sun in a direct manner, but because the Sun's massive presence has curved spacetime in such a way that Earth's path through spacetime is a stable orbit. Einstein's theory has been confirmed through numerous experiments and observations. One of the first confirmations came from the observation that light from stars bends as it passes close to the Sun, a phenomenon observed during a solar eclipse and precisely predicted by general relativity. More recent tests include the detection of gravitational waves, ripples in spacetime caused by massive objects like black holes and neutron stars merging, which were predicted by Einstein's theory and first directly observed in 2015. So, in the context of general relativity, gravity does exist, but not as a force. It exists as the curvature of spacetime caused by mass and energy, fundamentally changing our understanding of how the universe operates at both large and small scales. Does gravity actually exist? Yes or no? Yes, gravity does exist, but its fundamental nature is more complex than the traditional force concept. According to Einstein's theory of general relativity, gravity is a manifestation of the curvature of spacetime caused by mass and energy, not a force in the Newtonian sense.